Have you ever wondered how a simple machine under your kitchen sink can take tap water or even salty ocean water and turn it into pure, crystal clear drinking water? It's not magic. It's a brilliant piece of engineering called reverse osmosis. And by the end of this video, you'll understand exactly how it works. Hello, engineering minds, and welcome back to the channel. Today, we're diving deep into the science behind one of the most important purification technologies in the world, reverse osmosis, or RO. We'll start by understanding its natural cousin, osmosis. Then we'll see how we can reverse that process. We'll look at the special membrane that makes it all possible, walk through how a home water purifier works, and finally, explain how we use this tech to get fresh water from the sea. Ready? Let's get started. First things first. To understand reverse osmosis, we have to understand regular osmosis. Formally, osmosis is the natural movement of a solvent, like water, across a special barrier from an area of low concentration to an area of high concentration. Okay, what does that actually mean? Imagine you have a large room divided by a screen door. On one side, you have fresh, clean air. On the other side, you have smoky air. The screen door is our special barrier, a semi-permeable membrane. What happens naturally? The small, fresh air molecules will automatically move through the screen door into the smoky room to try and balance things out. But the larger smoke particles are too big to pass back through the screen. This natural tendency to move from a less concentrated area to a more concentrated area to achieve balance is the heart of osmosis. Nature doesn't like imbalance. Visually, think of a U-shaped tube. We have pure water on the left and salt water on the right, separated by a membrane at the bottom. Because of osmosis, the pure water will naturally flow towards the saltwater side, trying to dilute it. This actually causes the water level on the saltwater side to rise. The extra pressure created by this height difference is called osmotic pressure. This isn't just a lab experiment. It's happening inside you right now. Your body cells use osmosis to absorb water and nutrients. It's a fundamental process of life. So, osmosis is nature's way of balancing things out. But what if we don't want to dilute the salty water? What if we want to get the pure water out of it? Well, for that, we need to reverse the process. Reverse osmosis is a separation process that uses pressure to force a solvent through a membrane that retains the solute on one side and allows the pure solvent to pass to the other side. Let's go back to our smoky room analogy. Osmosis was the fresh air naturally seeping into the smoky room. Reverse osmosis is like bringing in a giant, powerful fan. We place this fan in the smoky room and turn it on full blast, pointing it at the screen door. The intense pressure from the fan physically pushes the small air molecules out of the smoky room, through the screen, and back into the fresh air side, leaving all the large smoke particles behind. We are literally reversing the natural flow by applying external pressure. In our U-tube, this is like putting a piston on the saltwater side. We push down hard. If we apply a pressure that is greater than the natural osmotic pressure, we overcome nature's tendency. We force the water molecules to move against their natural direction, from the salty side back through the membrane to the pure water side. This is the core technology inside that water purifier under your sink. It's also used on an industrial scale in desalination plants that turn seawater into drinking water for entire cities. Now, the real hero of this story is that special barrier, the membrane. So how does it work? It's a layer of material designed to be a molecular gatekeeper. Think of it as a bouncer at an exclusive club. The bouncer has a very strict guest list. Small, nimble water molecules, they're on the list. They can go right through. But larger, bulkier things like salt ions, bacteria, viruses, and other contaminants, they are not on the list. The membrane blocks them completely. It's a highly selective filter on a microscopic level. Imagine a sheet of material riddled with incredibly tiny pores. These pores are just large enough for water molecules to pass through, but too small for almost anything else. In a real RO system, this sheet is often rolled up into a spiral to maximize the surface area inside a compact cylinder. Besides water purification, semi-permeable membranes are critical in medical applications, like dialysis machines, which filter waste products from a patient's blood, a process that also relies on the principles of osmosis and diffusion. So, how do we put this all together to solve a massive real-world problem, like getting fresh drinking water from the ocean? Let's walk through it. The problem: how do we make seawater drinkable? Step 1, the challenge. Seawater has a very high concentration of dissolved salts. This means its natural osmotic pressure is enormous, around 25 to 30 atmospheres. To put that in perspective, the air pressure around you right now is 1 atmosphere. So nature really wants to dilute seawater. Step 2, the solution. To reverse this powerful natural flow, we need to apply an even more powerful external pressure. Industrial desalination plants use massive high-pressure pumps to pressurize the seawater up to 60 or 70 atmospheres, more than double the natural osmotic pressure. Step 3, the process. This highly pressurized seawater is pumped into vessels containing the spiral wound semi-permeable membranes. The immense pressure overcomes the osmotic pressure and forces the water molecules to do what they wouldn't normally do: leave the salt behind. Step 4, the result. 2 streams come out of the RO unit. One stream is the pure desalinated water called permeate. This is our drinking water. The other stream contains all the salts, minerals, and impurities that were left behind, now in a highly concentrated solution. This wastewater is called brine, or reject water, and it gets flushed away. It's important to remember that RO systems always produce this waste stream, which is a key environmental consideration. And just like that, through clever engineering, we have reversed a natural process to create the most essential resource for life. So let's recap quickly. Osmosis is the natural flow of water from a low concentration to a high concentration across a membrane. The semi-permeable membrane acts like a microscopic filter, letting only water pass through. And reverse osmosis uses high pressure to force water against its natural flow, separating it from contaminants and giving us pure water. From the glass of water in your hand to providing fresh water for entire countries, reverse osmosis is a technology that truly changes the world. If you found this explanation helpful, please give the video a thumbs up and subscribe for more engineering concepts made simple. And if you have any questions, drop them in the comments below. Thanks for watching, and we'll see you in the next one.